Hello students! Cello, today we are going to learn a very simple but super important topic from our unit on alternating current. We'll see what happens when we apply an AC voltage to a simple resistor. Now, understanding this properly is the key for the entire rest of the chapter, and don't worry, I will make sure this explanation is very clear and 100% exam safe for you.
Okay, let's dive in with a simple question about something you see in your house every day. You plug in an electric heater, right? And it gets hot. But have you ever thought about it? The AC current in our homes is reversing its direction forward, backward, 50 times every single second. So how on earth does it produce steady heat? Let's find out.
So how do we solve this puzzle of the heater? You know, the core idea behind it is actually very, very simple. The whole secret is in the perfect timing, the synchronization between the voltage we apply and the current that flows through that resistor. Now, the most important idea you need to remember is this. In a resistor, the voltage and the current are perfectly in sync. Just imagine this. When the voltage gives a push, the current immediately starts moving. When the voltage pulls back, the current immediately reverses. There is absolutely zero delay. You can think of them as best friends who do everything together at the exact same time.
This slide here, this graph, shows the relationship perfectly. Just look at the two waves. The voltage and current are like perfect dance partners. They are always in phase. See? They hit their maximum value together, they both cross the zero line together, and they hit their minimum value together. This, Butcho, is the single most important property of a resistor in an AC circuit.
So what does all this mean for the formulas we need for our exams? Well, I have some very good news for you. The rule you learned way back in class 10, it's still your best friend here.
So, the crucial point is that Ohm's law, which you already know so well, it works perfectly for resistors in AC circuits at every single moment. The instantaneous current is simply the instantaneous voltage divided by R. And the peak current? Well, that's just the peak voltage divided by R. Simple, isn't it? No change at all.
And this derivation here beautifully illustrates the logic. See, we start with the voltage equation, which we know is a sine wave. Then we just apply Ohm's law, I equals V by R. Now, since R is just a constant number, right, dividing the voltage by R doesn't change the sine wave's timing or its shape. It only changes its height, its amplitude. And that's exactly why the current must follow the exact same sine wave pattern as the voltage.
To make this absolutely concrete, have a look at this simple calculation. This is a typical board exam question. We are given the RMS voltage, that's the standard value for our home supply, and the resistance. We just use our familiar Ohm's law, but with the RMS values. So IRMS equals VRMS divided by R. That's 230 volts divided by 46 ohms, which gives us a clean 5 amps. See? It's that straightforward.
Okay, now for a very important part. Let's clear up some common mistakes, some common traps that students fall into during exams. This is where you can lose marks if you are not careful. So let's talk about power and heat.
You see, the power isn't constant. It actually oscillates as well. At any instant, power is just voltage times current. But since both V and I are sine waves, their product becomes a sine squared wave. Now, what's the most basic property of a squared number in maths? That's right, it's always positive. Remember this, beta. This is the answer to our very first question about the heater. A common mistake is thinking that when the current becomes negative, the power also becomes negative. No, not at all, because power is I squared R, and the square of any number, whether it's positive or negative, is always positive. So whether the current is plus 5 amperes or minus 5 amperes, the power dissipated is exactly the same. The resistor is always getting hot. Its only job is to give off heat.
This is another common trap. Students hear the term alternating current, and they think everything in the circuit must be alternating. But no, the resistance, R, is a property of the material itself, its length, its area. It is rock-solid constant. It does not care if the current is AC or DC. It just resists, always.
So chalo, let's quickly summarize what we've learned and more importantly, see why this simple idea about the resistor is so critical for the next topics we're going to study, like inductors and capacitors.
So here's the big picture, the main takeaway. The resistor is our simple 0-degree reference point. You should think of it as our baseline. Now, why does this matter so much? Because when we study inductors and capacitors next, you will see they behave very differently. They actually introduce a delay, what we call a phase shift between the voltage and current.
So to understand that shift, you must first perfectly understand our zero-shift hero, the simple resistor. So, to quickly recap for your exams, just remember these key points. 1. In a pure resistor, AC voltage and current are always in phase. 2. Ohm's law, V equals IR, applies at every single instant, whether you're using instantaneous, peak, or RMS values. 3. Resistance, R, is a constant and does not depend on the AC frequency. And 4. A resistor always dissipates power as heat, meaning power is always positive because of that I-squared term. Master these ideas, and you are perfectly ready for the challenge of inductors and capacitors.